x squared right there. And then you find out that 2 du is equal to 4 dx. So we liked writing it as dx is equal to 2 du over 4x. So you do that substitution. You do the substitution, and you end up with 2 times e to the u du. So the integral of that is 2 e to the u plus c. Plug everything in, and you end up with that. What were the specific stopping points? I made it so that you could substitute into for the entire 4x dx. Here is 4x dx, but what is that equal to? 2 du. So the 2 and the du are there instead of the 4x dx. It's just a different type of substitution. It's just a different type of substitution. You end up in the exact same place if you did the way we'd normally done it, but that's just a different way of setting it up. That's it. Does that make sense now? Yep. Do this out like this, and we say w is equal to the square root of x, which is x to the what? 1/2. What does dw dx equal? Not a rhetorical question. 1/2 x to the negative 1/2, right. So dw is equal to 1/2 x to the negative 1/2 dx, like this. So what does dx equal? dw over 1/2 x to the negative 1/2, which is the same thing as 2 dw over x to the negative 1/2, correct? We can simplify that further, though. X to the negative 1/2 in the denominator is the same as x to the what in the top? 2x to the 1/2 dw, exactly. So we now know that dx is equal to 2x to the 1/2 dw. That is the key thing you have to figure out in this question, because when you now make the substitution, you make those two substitutions right there, what do you get? Integral sine of what? Sine of w over the square root of x. Instead of dx, what do we write? 2x to the 1/2 dw. What's the magical thing that cancels now? What's the magical thing that cancels, Lizzie? Take a look at the board. What cancels now? The x to the 1/2, right. So you're left with the integral of sine w, 2 on the outside, dw. Yay. Cancels nicely, but the key is right here. This is the key, getting to this right here. Notice how I didn't put in the limits of integration? What should I put in instead? These are now w values. What does w equal? The square root of x. What's the square root of 1? So it's the square root of 1 and the square root of, what goes up here? The square root of 3. So that is the integral you are now integrating. Yes, Lizzie?
Not to be annoying, but could you put this in our notebook here in the B period one?
Ah, is it? So let's finish this. So what's the integral of sine? What's the integral of sine? Negative cosine of w from 1 to the square root of 3. So what's that going to be? 2 times negative cosine of root 3 minus negative cosine of what? 1. And what's the only thing you can do to simplify this? Negative 2 cosine square root of 3 plus 2 cosine 1. Are those trig values that are nice? No, they are not. That's where you would stop. That's where you would stop. Very important here. These values right here, Nick, are the ones we started with, the 1 and 3. Are those x values or w values? Those are x values. What are we in now? What are we in now? W values. You have to translate them into w values. What's the relationship between w and x? W is the square root of x. So these are x values right here, the 3 and the 1. So how do you go from how do you turn those into w values? What do you do to each of them? You square root them, exactly. W is equal to the square root of x, so it's going to be the square root of 1 and the square root of 3. That's where they come from. How did I do, kids? Those of you that are talking, stop for a sec. Is this what your picture looks like? Yeah. Now, did I do this to scale? No. Should you do it to scale? It doesn't matter. I would prefer you don't, because it's going to be real steep. It's going to be hard to draw. What points are really important to find on this? Well, have I labeled all the important things? What do you think? Are there any other important things I should label? Points are? Yeah. Yeah, they could be really helpful. Sure. So you want like the intersection points, like there and there. So that's going to be 4, 20, right? And negative 2, what? 8. That could be helpful, absolutely. And it says, find the area between the x-axis and the curve. So can someone tell me what the integral I'm going to need to evaluate is? What's the integral? Yeah.
Integral from negative 2 to 4.
Okay, stop for a sec. Of what? Can someone tell me what comes next? What's it the integral of, Jen?
X squared plus 4.
Yep, x squared plus 4. Then what? There's something missing right here. Yeah. dx. Is there anything else I need? Is there anything else? No. Nope. So if you had your calculator, you could punch this into your calculator and get it. But if you didn't have your calculator, you could just write it as, well, what's the integral of x squared plus 4, Jen? Common mistake is on this one? What do you think the most common mistake is? The negative signs, absolutely. You have a negative cubed. So what do you have here? You end up with 64 over 3 plus 16 plus 8 over 3 plus 8. So what is that? 72 over 3 plus 24. Is that correct? So yeah, 24. So what is that? 72 over 3 plus 72 over 3, right? I think that's it. So you have 144 over 3. That would be the exact answer. That would be the exact answer. Exact answer. I think so, yeah. 144 divided by 3. What do you get? 4, 12, 2, 4, 8. Yeah, it's equal to 48. Absolutely. Good job. Not a circle because it's going to be a parabola in the base. Kind of looks like that. I shaded it a little too much, but that's what it looks like. So that's the region. When it says bounded by, it means a barrier. Like a fence is a bound. A fence is a bound, Henry. So we're looking at that right there. My question to you is, there are 2 points I haven't labeled. What are those 2 points that I need to label, and where are they? What do you set equal to what? Yeah, set 1 is equal to what? The other. So it's x squared is equal to 6. So x is equal to plus or minus what? The square root of 6. So then once you have x, you need to find what? Well, we know what y is. It's 2. So what's that point right there? The square root of 6 comma 2. And what's this one right there? What's that one? Negative square root of 6 comma 2. So we have all the information we need to write an integral that represents the area. Draw the rectangles in. If you were to draw the rectangles in on this one, where would that rectangle be? It would be right here. What's the height of that rectangle? What's the upper part of that rectangle? 2. What's the lower part? X squared minus 4. That's the upper minus lower. And what's the width of that rectangle? What's the width of that rectangle? What did we call this right here? That's dx. And what's the height of the rectangle? 2 minus x squared minus 4. So is that something you can simplify? Yes. If I gave you a calculator, could you figure that out exactly? Absolutely. So what would this simplify to? The integral of negative root 6 to the square root of 6. The integral of what? Negative 2. Oh, no, not negative 2. What is it? 6 minus x squared dx. Nick, what's the integral of 6 minus x squared? What's the integral of 6 minus x squared? Minus x to the... Yeah, and you're doing that from negative root 6 to positive root 6. So what do you get there? When you plug in square root of 6, you get what? 6 root 6 minus the square root of 6 to the what power? To the what power? 3, because you're plugging it into that function all over. 3 minus 6 times what? Negative square root of 6 minus negative square root of 6 to the third over 3. Is this kind of annoying to do?
Yeah.
It is. Is each piece not that bad? Each little piece isn't that bad, but again, Jen, as you answered before, what's the most difficult part of this problem, really? Keeping track of the negatives, absolutely. So if you were to simplify this, what do you get? 6 root 6 minus, you have to be careful, it's root 6 times root 6 times root 6. What is this? It's equal to 6 root 6. So what is that? 6 root 6 over 3 plus 6 root 6. And then how many, is it negative or positive in the next thing? What do you think? It's plus 6 root 6 over 3. So what do you have here? How many 6 root 6s? You have how many there? That's 12 root 6s, right? And then what is this? Minus 6 root 6 over 3 plus? Oh, that's 6 root 6, right?
Yeah.
Correct? So what happens to those two terms? That cancels there, and you're left with just 12 root 6. That is the exact answer. That is the exact answer. Yep. How to get what? Do right now is draw this for me on a set of axes. Draw that for me. That's all I'd like. Okay, it's a little hard to see, but how did I do there? I made the axes purple. I had to change colors there. How'd you guys do? Did you do pretty well? Yeah, something like that? Okay, so look what this question says. This question says, let's erase this now. Find the volume of the solid. Everybody stand up for a second. I need you to really pay attention to this and write nothing down. Find the volume of the solid of revolution that is generated by rotating the region bound by the given curves about the indicated axis. So it's bound by, we want to rotate it around the x-axis. So we have y equals 5, x equals -2, and x equals 4 right there. It says find the volume of the solid of revolution that is generated by rotating the region bounded by the given curves about the given axis. Be sure to draw a sketch. So what we're doing in this one is, are you okay with each of these vertical and horizontal lines? You see where they come from? Yay? What we're going to do is we're going to take this shape right here. We're going to take this shape right here, and we're going to rotate it around which axis? The x-axis. So we're going to rotate it around like this. So what shape is that right there? What is this shape? It's a what? It's a rectangle, right? It's got a width of 6 and a height of 5, so it's a rectangle, right? You're going to take a rectangle and you're going to rotate it around the x-axis. You're going to rotate it around the x-axis. What shape, raise your hand, don't say it out loud, what three-dimensional shape are you going to make when you rotate that rectangle? Think of it in your head, you have a rectangle floating in space right here, and you rotate it around the x-axis. What shape are you going to get? Raise your hand when you can think of it. What do you think you're going to get? A what?
A donut.
Well, where's the hole going to be? Is there going to be a hole? So if we have, I'm going to turn it on its side right here. Here's that rectangle. And what are we going to do with it? We're rotating it around this axis, the x-axis, so it's going to go like this. This thing is going to, it's a really terrible marker. So then you're going to turn it a little bit, right? And it's going to look like this. You're going to turn it a little bit, it's going to look like this, right? It's going to look like this, so it's going to go like this. So what are you going to make? What are you going to end up with? It's a three-dimensional shape, so what is it going to be? It's a cylinder. It's a cylinder. Imagine you had a piece of paper right here. Imagine this was the rectangle. Everybody sees the rectangle right here? What happens when I spin it? What shape am I going to get? If I spun this a million miles an hour, what would you see? You would see a cylinder. A circle is a two-dimensional object, everybody. Stop saying circle, okay? Three-dimensional object has depth, width, and height, correct? So if I keep on spinning this like this, what am I going to make? A cylinder. Exactly, a cylinder. So what's this question asking you about? Is it asking you for area?
No, volume.
No, it is asking you for volume, which is a different ballgame. Okay, you can sit down now. So we're going to have a cylinder that's going to look like this. Yay! It's going to look like this. And and that's a terrible cylinder right there, isn't it? Man, that is a terrible cylinder. What's it going to look like? It's going to look like this. You trolling me? You trolling me, Kira? You trolling me? So there's our cylinder right there. I'm trying to make it like that. Like this. There we go. That's better. Where is the original rectangle, everybody? It's inside it, right? There's your original rectangle. There's the original rectangle. Now, can you see the three-dimensional shape I'm trying to draw right there? Everybody sees it? Okay, so this is the center right here. So that would be this point, right? This would be the x-axis right here. Everybody sees the x-axis? Nice, there's the x-axis. What's the radius of this cylinder going to be? What's the radius? What's this height going to be? It's telling you it right. It's 5, exactly, Nick, exactly. What's the height of this cylinder, Henry? What's the distance from here all the way to here? What's this distance going to be?
4.
Nope, close. Close.
6.
It's going to be 6. Why is it 6?
Use -2 to 4.
-2 to 4, so it's 6. So that is a cylinder. That is a cylinder with a radius of 5 and a height of 6. Do you remember what the volume of a cylinder is? The formula for a volume of a cylinder?
Isn't it circumference? Sorry.
Pi r squared times the height. In this case, the r is what? You just told me. It's right there. 5. And what's the h value? 6. So what's the volume of this thing going to be? Pi times 5 squared times 6. That's 25 pi times 6. So what is that? 150 pi, whatever units cubed, whatever they are, square inches, cubic inches. Point being, you can take things and you can rotate them to get shapes, three-dimensional shapes that you've seen before. Here's a side note, not a side note, but let's say I gave you this shape right here. What shape is that? So let's say this was the y-axis right here. Everybody sees the y-axis? What happens if I rotated that around the y-axis? What shape would I get if I rotated this around the y-axis? What shape would I get? Yeah, you would get a cone. Is it sitting on my desk? Oh, look, it is sitting on my desk right here. Look, here's a cone. If I were to slice this down the middle right here, what would you see? You'd see a triangle. And if I cut it again in half, you would see this. If you took that and spun it around, this is what you'd get right here. Everybody sees that right there? Everybody sees that? So what you end up doing, everybody, what you end up doing is you end up, instead of adding up rectangles, you start adding together slices. So let's go back to this one for a second right here. Let's go back to this one. If you were to slice this into, remember the rectangles we sliced it in before? See all those rectangles? What's nice about all these rectangles? They're perfect, they're the perfect area, right? They don't actually go up or below because it's a straight line. What happens if you spun one of these? You get a cylinder. It'd be very skinny, right? What happens if you spun the next one? You'd get the same thing, right? You would get the same thing. So we're going to try to set this up as an integral here. We're going to try to set this up as an integral. What's the volume of a cylinder, Nick? What's the volume of a cylinder? What's that formula? Pi r squared times what? Height. Pi r squared times height. Pi r squared times height. So on this one right here, we're going to integrate this. There's a problem though. How many variables did I just write? How many? You can count them. R, H, and X. How many variables is that? 3. We'd really like it just to be with what variable? Yeah, just one variable, X, right? What's the height of this entire thing? What's the height of this entire thing?
6.
The height is, we think it's 6, right? Something like that. So let's make it even easier and break it down into one of these. If I were to spin one of these, what's the width of one of these? What did we call the width of one of these in the integral symbol? What that width was notarized by what? D what?
Yeah.
Each of these widths was dx, correct? Each of the widths was dx. So if I were to spin just this one, if I were just to spin this one right here, it would make a cylinder. Do you agree, Jen?
Yeah.
If you just spun one of these, it would be a really skinny cylinder. Are you with me? It would make one cylinder right here. Do you agree? Right? That is the height of that cylinder. Do you agree? It's very small, but it's the height of that cylinder. What's the radius of this cylinder? Well, it says it right there. What's the radius of this cylinder right here? 5. It tells you it right there. It goes from 0 to what? 5. All of these have a radius of 5. All of these have a radius of 5. So what was the area of a cylinder? Pi r squared times what? Height. But for each little tiny cylinder, this h was dx. And what was r equal to? 5. Yes. Are you with me so far?
I don't really understand why the radius of each little cylinder is 5.
Because every single one of them has a radius of 5. This doesn't change because I'm telling you it's 5. In this picture, r stays the same the entire time. The radius stays at 5 the entire time. So for each little tiny one, you have pi times 5 squared dx. This represents the volume of one slice. How many slices are there total, though? A lot. What's the proper way to say a lot in math? An infinite number of them. What did we learn how to do with integrals? How many rectangles did we add together when we used the integral symbol? An infinite number of them. So we're actually integrating how many of them? Starting at what? Negative and going to 4 of what? Pi times 5 squared dx. Let's see what this equals. Let's see what this equals right here. So if we do this right here, what can we factor out to the front? Yeah, no, what'd you say? Yeah, so what does that equal? 25 times the integral from negative 2 to 4 of what? Pi, excuse me, it's just what? Pi dx. Could we factor out the pi as well? Is that allowed? Can we factor out the pi? Sure. So what do we have here? 25 pi integral from negative 2 to 4 of what? Dx. Are you with me so far? What's the integral of just dx, Nick? What's the integral of dx? Effectively, what's the integral of 1? What's the integral of 1? Just 1x. So what is that going to be? 25 pi times x evaluated from negative 2 to what? 4. So that's 25 pi 4 minus negative 2. What's 4 minus negative 2? 25 pi times 6. What's 25 times 6? What did we get? The same exact thing. You just proved that the area of a cylinder is pi r squared times height. So there are two things. You have formulas that you knew from geometry. What are some formulas you know from geometry? What's the area of a circle? Pi r squared, right? What's the area of a cylinder? Pi r squared times height. Have we ever proved those before? No, you just get to use them. So sometimes when you rotate things, are you going to get shapes that you've seen before? Let's say I took a half circle and I spun it. What would I get if I took a half circle and I spun it? You would get a sphere. Is there a formula for spheres? Yeah, 4/3 pi r cubed. Do we have any idea where that came from? Guess what we now get to prove? Where they come from. And volumes of lots of other shapes. Because what can functions do? Use your hand to show me what a function can do. What can a function do? Anything you want. So you can take a function that looks like this, and then what could you do with that function? Spin it. Has anybody worked with throwing like a pot or used a lathe before with wood? It spins, and you put a little blade down, and you can make it do whatever you want. You can turn it into a baseball bat, right? Or a vase that does just about anything you want. We are now going to figure out how to find the volume of rotational solids. Are some rotational solids relatively straightforward? Yes. Are others not? Not. That's correct. So, a straightforward function. Let's do this one right here. It says y equals 2 times 3 to the x equals 1, x equals 4. Everybody stand up. I'm going to do this one out. Actually, I'm going to run and see if I can get the charger before it dies. So 2 times 3 to the x. How would you go about graphing that by hand? Plug in what number?
0.
Yeah, what's 2 times 3 to the 0? 2. Is this a line?
No.
No. What does it look like? Use your hand. It goes pretty steep, right? So let's just make it steep like this. Well, here's x equals 1, and here's x equals 4. So we're going to take this shape right here, and what are we going to do with it? We're going to twirl it about the x-axis. So if you were to twirl this around the x-axis, what would it look like all the way down? It would, the flip side of it would look like this. I'm trying to do my best on the reflection here. It would look like this, right? And you would get concentric what? You get circles. Does everybody see what this kind of would look like?
No.
Take the yellow. Are you being sarcastic or you can't? I can't tell.
No, I didn't realize that.
Is it, look,
Oh wait, it's kind of like a
it's
funnel.
going this way.
Okay.
It's going this way. Does everybody see what's going on here?
And
And it would go like this. It would also go around the other side. Does everybody see how it would go around to the other side too? This is just the front half of it. Yes, the cut off volcano.
Oh yeah.
Everybody sees it now, like this. Everybody sees the volcano.
I really have to go this way.
Yeah. Now do you see it?
Yeah.
As a side note, will we rotate around the y-axis too? Sure. Doesn't change the math very much. But the point is, what do you see right here? What shape is this? A circle. What shape is this one going to be? These are all going to be concentric circles, right?
Yeah.
These are all going to be concentric circles. What do you think the lower limit of integration is on this one? It's right there. 1, and you're going all the way to?
4.
And you have pi r squared, and the h for each of these is dx. Remember, each height, the height of each slice is dx. What do you think the radius is going to be on this? Keep in mind, what's this function? Y equals what? 2 times 3 to the x. So this to this represents the what of each slice? The radius of each slice. So we have 1 to 4 of pi times what? 2, 3 to the squared times. How many variables is that?
1.
That's one variable. Do you know how to integrate something like that? Absolutely. What you've written is an infinite number of disks being added together. The volume of an infinite number of disks added together. What are the first two numbers you can... what do you have to do first if you're going to do this by hand? Would you guys know how to do this by hand? Simplify. So what do we simplify first? What can we pull out? Pi. You can't pull out 2 pi actually, because what do you have to do first? Square it. So that's going to be 2 what? 3 to the what power? 2x dx. Now what can you factor out? 4. So that's going to be 4 pi, the integral from 1 to 4 of 3 to the 2x dx. Do you remember what the integral of 3 to the 2x dx is? What's the integral of 3 to the x? Do you remember what that is?
1 over ln
3 to the x over
3
ln.
times
No.
3x.
Because when you take the derivative of 3 to the x, you get ln 3 to the x, so you have to cancel that out, right?
Yeah.
What's the only difference here? It's a 2x, right?
Chain rule.
The chain rule would kick out a 2. So if you're going to do the integral of 3 to the 2x, what's that going to be? 1 over what?
ln 2 ln
2 ln 3, 3 to the x plus c. Why is it 2 ln 3? Because the 2 will come out with the chain rule. You need to cancel the 2. So if you want to cancel the 2, you have to put it in the denominator. So what is this integral going to be? 4 pi times what? 1 over 2 ln 3, 3 to the 2x. And do we care about the plus c because this is definite? From 1 to what? 4. Let's keep going here. We have 4 pi times, plug in 4, what do you get? 1 over 2 ln 3, 3 to the what power? 3 to the what power? 8 minus 1 over 2 ln 3 times 3 to the what? 2. What could I factor out of both things there?
4x or 4 pi?
4 pi. Thank you, Nick. I'm not putting an x back in. We wanted to get rid of the x, right? My fault. What can we factor out of both of these terms?
1 over 2.
Yeah, exactly. So what do we have here? 4 pi over 2 ln 3 times what? 8th minus. There's only one more thing we could factor out. What could we factor out now? 3 to the 3 squared, and we could change that to 2, right? So what do we have here? 2 pi times 3 squared all over ln 3 times what? 3 to the what? 6 minus 1. Whew! What's 3 squared?
9.
So we have 18 pi times 3 to the 6th minus 1 all over ln 3. Boom.